Place one hand on a steel worktop and the other on an oak table. The steel will bite into your skin. It feels drastically colder, but it's an illusion. Both surfaces have been sitting in the same ambient air for hours. Thermodynamically, they are exactly the same room temperature. Despite this, design teams routinely treat perceived warmth as a superficial finish. They try to solve a cold surface by specifying a matte lacquer, a warmer color palette, or a softer texture. Those surface treatments fail because the physical sensation a user feels is actually locked in the moment a specific material is chosen, often for structural reasons like rigidity, weight, or cost. If our nerve endings aren't actually measuring the temperature of the room, we have to look at what they are reporting and why trying to fix that sensation late in the process is a costly mistake. The sensation we call cold is governed by a specific physical property, thermal effusivity. This equation represents thermal effusivity, multiplying thermal conductivity, density, and specific heat capacity. It dictates the exact rate heat migrates from a hand into a material. Aluminum conducts at 236 watts per meter Kelvin. Softwood sits around 0.14. Aluminum moves heat 1,000 times faster. There is a countermetric pulling the other way. Specific heat capacity measures how well a material stores thermal energy, and per kilogram, wood actually hold heat much better than metal. But storage capacity cannot rescue the wood. Human touch is strictly a transfer problem, not a storage problem. Wood physically cannot move the heat fast enough to drain it from your hand. Because your skin is warmer than the surface, heat leaves at whatever rate the material allows. As the metal rapidly pulls that heat away, the skin's local temperature drops, and your nerve endings report that sudden loss. What people describe as coldness is entirely a mathematical rate. That makes the perceived warmth of any product a pure physics decision, one that gets made at the concept stage whether anyone notices or not. You see this physics principle most starkly in environmental design, particularly flooring, where the consequences of thermal effusivity are impossible to ignore. If you look at thermal resistance figures, deep pile carpet with underlay scores around 0.25 square meter Kelvin per watt. Hardwood drops to 0.10. Ceramic tile sits at a flat 0. Because tile has such high conductivity, it is highly efficient at delivering heat from an active underfloor system. But that exact same property guarantees the floor will feel freezing underfoot the moment the system is turned off. At the extremes, this shifts from a comfort issue to a biological hazard. NASA established strict touch temperature limits by testing materials in controlled environments to see when human skin sustains damage. Their data shows pain onset occurs when the skin interface hits 44 degrees Celsius. Cold pain begins around 15 degrees, numbness sets in near 7, and the risk of frostbite begins at 0. U.S. safety regulators translate these thresholds into plain warnings for outdoor spaces. Bare metal equipment sitting in direct sun can cause contact burns in seconds, while wood in that exact same sun remains safe to touch. The environmental temperature is identical. The solar exposure is identical. The material's thermal inertia is the sole variable determining whether a hand experiences a comfortable surface or a severe burn. This brings us back to the heavy, permanent reality of the manufacturing floor, where theoretical science becomes a physical object. Effusivity is a property of the material's bulk. Aesthetic finishes like paints and lacquers are merely microns thick, meaning they have almost no impact on the thermal transfer rate. If you specify a handle in carbon steel to achieve high structural stiffness, it will invariably feel cold in an unheated room. No layer of paint can overcome the physics of the bulk metal underneath. Engineers are often forced to implement late-stage workarounds to fix the sensation. They wrap the metal in thin insulating skins. They cut deep knurls to reduce the surface contact area with the hand, or they install active internal heaters. Every single one of these additions is an expensive, retroactive repair for a material decision that was made poorly at the very beginning of the project. Intelligent design means selecting a material with precise foresight of what the human hand will feel and making that choice early when changing your mind costs nothing. Whether you are running thermal lab simulations or visualizing exact aesthetics with Depix, early decisions are as cheap as a sketch, but they become brutal once tooling begins. You have to see every angle before you build.